Okay, so for the rest of this class's lessons, we're going to look at this notion or this idea of permutations and something called combinations. But before we do that, I want to make sure that you're comfortable with this notation that you may or may not have seen before. And the notation looks like this. You might see this n factorial. And the definition of n factorial, if you have any number factorial, that's what that exclamation point is. That means that you're going to multiply that number by that number minus 1, that number minus 2, that number minus 3, and all the way down until you hit 1 as your last integer value. So for example, 4 factorial, well, the expanded form of 4 factorial is the same thing as saying 4 times 3 times 2 times 1. And that's equivalent to saying 12, 12 times 2. And that's the same thing as saying 24. Okay, so one more example. Let's say that we have something like 10 factorial. Let's do 10 factorial. We'll do 8 factorial. Well, 8 factorial is the same thing as saying 8, excuse me, times 7, times 6, times 5, times 4, times 3, times 2, times 1, and I'm going to need my calculator to help me out with this one. And you'll check your calculators. Some of your calculators will actually have these functions on it. But I end up getting, when I multiply all these together, 40,320. So that's for 8 factorial. And by definition, there is something that I need to bring up, because we're going to see this in a little bit. Anytime you see 0 factorial, that's equivalent to saying 1. That's just by definition. And the proof of it is fairly easy, but kind of not within the scope of this class to discuss. So here's what we're going to do. We're going to talk about something called permutations. You may have heard that word permutations before. How many permutations are possible given some type of situation? And permutations, that's what that big P stands for over here. This is the formula for permutations. If you have n objects, so let's say you have a bunch of objects, we're just going to say you have n objects, and you want to take a handful of those objects out of the total amount you have. So if you have 50 objects and you want to take 3 of them, if you have 200 objects and you want to take 150 of them. For example, my kids have like $15, and when we travel, I say you can choose $2 to take on vacation with us. So n is going to be your large value. You have n objects available, and r of them are selected, right? So we have $15 and we're selecting 2 of them. You have 100 books and you want to figure out how to select 5 of them. So the formula for permutations is you have n objects and you're taking r of them is the same thing as saying n factorial divided by n minus r factorial. Let's just do one quick example. So for example, if I have 5 objects and I want to select 3 of them, well, the formula for that would be, so our n is this first value over here, 5 factorial divided by, denominator over here, n minus r, 5 minus 3 factorial. Well, let's simplify this. So 5 factorial, that's the same thing as saying 5 times 4 times 3 times 2 times 1. 5 minus 3, well, that's the same thing as saying 2. So 2 factorial, that's the same thing as saying 2 times 1. Now, there's a few different ways in which you can handle that if you want to figure out what the numerical value is. You could multiply all terms in the numerator or multiply all terms in the denominator. So for here, we would get 20 times 6 times 20 times 6 is 120 times 1, 120 in the numerator. 2 times 1, which is 2 in the denominator. So we would end up getting 60. But what you could also do, and I don't know if you guys remember this when you're talking about fractions or not, you could cancel out the factors that are the same in the numerator and denominator. And we're just left with 5 times 4 times 3. Well, 5 times 4 is 20, times 3 is 60. So you get the same thing. So this is if we're dealing with something that are called permutations. And when we talk about permutations, we're talking about this idea that order matters. And in permutations, you cannot repeat. So repetitions are not allowed. So let's talk about what that means when we say this idea that order matters. Okay, let's use the letters ABC to find all possible ways to list 2 of these letters where order is important. So what that means is that AB, where order is important, that AB and BC, excuse me, and BA are considered to be two different things. Now, there are some cases where A, B, and BA are the same, and there are other cases where A, B, and BA are different. But let's answer this question, then we'll talk about and we'll talk about when they're the same and when they're different. Okay, so we have 3 items, and we want to figure out all ways to select 2 of them, or how many possibilities there are to select 2 of them. Well, okay, let's see. We could select AB. We could select AC. We could select BA. Remember that these 2 are different. We could select AB. We could select, what else are we missing? We could select AC. Excuse me, we selected AC already. Let's erase that. We could select BC. And we could select CB. So what that means is using the letters ABC, find all possible ways to list 2 of these letters where order is important. Here are all of the possible ways. And if we sum these up, I hope you can see that we have 6 total ways in which we can do it. Okay, so let's talk about what that means, the 6 total ways in which we can do it. If we take 3 things, and if we select 2 of them, where order matters or order is important, well, then we get 3 factorial divided by 3 minus 2 factorial. And that's the same thing as saying 3 times 2 times 1 divided by 3 minus 2, which is 1 factorial. And 1 factorial is just 1. And you can see 3 times 2 times 1 divided by 1. Well, 3 times 2 times 1 is 6. And 6 divided by 1 is 6. And these are the 6 possibilities: AB, AC, BA, AB, BC, and CB. So in this case, and we're going to come back to this idea of, again, why order is important and why order isn't important. I want you to think about times when you're listing things in order is important. For example, if you're doing your PIN, and assuming that repetition is not allowed in your PIN, right? Because here it says repetitions are not allowed. And normally repetitions are allowed, but if repetitions are not allowed, if your PIN is something like 1432, then it won't read it the same as if you put in 4321. The order in which your PIN, the order in which you put your PIN in is important. Same thing with your social security number. If your social security number begins with the digits 358, and if you try to input the digits 853, these are considered to be, 853, these are considered to be 2 different values. So again, we're at that case where order is, sorry, my pen's acting up a little bit, where order is important. So when we say where order is important, that means order matters. So BA and AB are 2 different things. 1432 and 4321 are 2 different things. All right, so let's take a look at this example over here. And for our first example, we have, there are 10 people taking place in a spelling bee. How many ways can we award a first, second, and third place prize among the contestants? Well, let's take a look at this. This is an example of a permutation, and I want to make sure that you understand why order is important. Because if, let's say, Bobby, Jamie, and Melissa are called, so they stand at the top of the stage, they stand at the podium and they say, okay, the winners of this tournament are Bobby, first place, Jamie, second place, Melissa, third place. Well, that's very different than saying Jamie, Melissa, and Bobby, right? Because the order in which they call them out tells you if they're first place, second place, or third place. This would be first, second, third, which is different than this if this was first, second, and third. So order is important here, right? The order in which they list them tells you if they're first, second, or third. Here, Bobby's first, here, Bobby's third. So this is an example of a permutation. And we have 10 objects. There are 10 people taking place in a spelling bee, and we're choosing 3 at a time because we have first, second, and third. So for 10p3, that's the same thing as saying 10 factorial divided by 10 minus 3 factorial. Oh, excuse me, see if we can fix this. Sorry guys, my dog is going crazy. Boozy, come here. Come here. Quiet up. 10 minus 3 factorial. Okay, so 10 factorial is the same thing as saying 10 times 9 times 8 times 7. Whoa, my pen is going a little crazy over here. times 6 times 5 times 4 times 3 times 2 times 1. There's my 10 factorial. 10 minus 3 in the denominator, that gives us 7. So we have 7 factorial. And 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And again, using that fundamental principle of fractions that you guys hopefully have learned before, we can cancel out the factors that are the same in the numerator and denominator. So we can cancel out the 7, 6, 5, 4, 3, 2, 1. And we're left with, in the numerator, just 10 times 9 times 8. And that gives us a total of 720 ways to do this. So 720 ways to do this. Okay, so there's a good example of a permutation. Well, let's talk about how we would compare permutations with combinations. Well, in combinations, it's very similar insofar that we have that n and that r. In combinations, we have a total of n objects, and we're taking r of them, just like in permutations, right? You have n objects, and you're taking r of them. But when we're dealing with combinations, order isn't important. And again, we're going to go back and talk about that in 1 second. So let's take a look at this example here, and it's the same example we had above. It says, using the letters A, B, C, find all possible ways to list 2 of these letters where order is not important. So what that means is AB is the same thing as BA. So we're not going to list them twice because they're considered to be the same thing. Okay, so AB. I'm just going to go up and look at the permutations that we listed already for this. We had AB, AC, BA, AB, AB, AC, BA, CA. We could do BC and CB. Well, let's cross out anything that's a double. So anything that's the same, but the order is different. So these two, I'd cross out this guy because these two are considered to be the same. Same thing here, if we compare these two, I'd cross out this guy because AC and CA are the same. Same thing here, we're going to cross out one of them because BC and CB are the same. So we only have a total of 3 of these possibilities. 3 possibilities where we want to find 2 ways to list the letters where order is not important. All right, well, let's use this formula to show that we have 3. So we have 3 things, and we're taking them 2 at a time. So we have 3 factorial divided by, so r factorial, right? R factorial, it's that value over here, so divided by 2 factorial times 3 minus 2 factorial. Okay, so that gives us, in the numerator, we have 3 factorial, which is 3 times 2 times 1. In the denominator, this 2 factorial is 2 times 1 times 3 minus 2, which gives us 1 factorial, which is times another 1. So 3 times 2 times 1, that gives us 6. 2 times 1 times 1, that gives us 2, and 6 divided by 2 is 3. So when we're dealing with combinations, what you do is you cancel out all those doubles if you have 2, or triples if you have 3, or quadruples if you have 4. And again, in combinations, we really want to remember that order is unimportant or order doesn't matter. Okay, so let's take a look. Let's take a look at this example over here. So you have 65 books in your bookcase. You can choose 3 of them to take on your next trip. How many different ways are there to choose 3 books from the 65 that you have in your bookcase? All right, so choose 3 books from the 65 you have in your bookcase. Now, I want to make sure that you understand this. If you choose 3 books, right, and if the books you choose are A, B, C, even if you choose the books in a different order, B, C, A, or if you choose the books in the order C, A, B, you're still choosing the same 3 books. That's what we talk about when we say that order doesn't matter. And these are all considered to be the same because I'm still choosing that 3 groups of book. The order in which we choose them is unimportant. That's why this is a combination and not a permutation. Okay, so the formula for combination says NCR, so we have n objects, and we're taking r at a time. So it's n factorial divided by r factorial times n minus r factorial. So n factorial, which is 65 factorial, divided by r factorial, so that's 3 factorial, over, times 65 minus 3 factorial. Okay, So there's some tricks to these types of questions that I want to make sure that you know how to handle them. 65 factorial, you ready? We're not going to write out 65 all the way down to 1. Don't worry about it. We're going to use some tricks. So 65 times 64 times 63 times 62 times 61 times 60 times ... We're just going to do this all the way down to 1. 3 factorial, 3 times 2 times 1 times, well, 65 minus 3, that gives us 62, and 62 factorial is 62 times 61 times 60 times 59 times 58. And again, we're going to do the same thing. We're going to say times ... all the way down to 1. Okay, fundamental principle of fractions says, once again, that we can cancel out the factors that are the same in the numerator and denominator. Now remember, in between all these dots is 59, 58, 57, 56, 55, all the way down to 1. Same thing over here. So you see this 62 cancels with that 62. This 61 cancels with that 61. This 60 cancels with that 60. Remember, all of these numbers are the same down to 1. So it's equivalent to saying, or it's the same thing as saying 65 times 64 times 63 all over the denominator. Now we just have 3 times 2 times 1, which is 6. So I'm going to use my calculator to help me out with this one. 65 times 64 times 63 divided by 6. And we have a total of 43,680 ways to do this. Okay, let's take a look at some examples. And I want you just to take a minute or two to read question numbers 1, 2, and 3. Okay, identify if this is the fundamental counting principle, if this is a permutation or a combination. Okay, let's take a look at each one. We select 5 toppings for your pizza from a total of 32 toppings. How many ways are there to do this? So we have 2 values. We have an N and we have an R. And the question I want to ask, the question I want you to ask yourself, is this an example of a combination or a permutation? Is order important? Well, think about it. If you select, let's say, onions, peppers, what else do people put on theirs? Olives, some extra type of cheese, and tomatoes, the order in which you select them is unimportant. You can do tomatoes, cheese, olives, onions, etc. So this is an example, this first one over here is an example, because the order is unimportant, of a combination. So what are we doing? Well, we want to figure out what 32, we want to figure out what 32 C5 is. Okay, so that's the same thing as saying 32 factorial divided by 5 factorial times 32 minus 5 factorial. Well, again, 32 factorial is 32, 31, 30, 30, 29, 28, 27, ... all the way down to 1. 5 factorial is 5 times 4 times 3 times 2 times 1. 32 minus 5, that's the same thing as saying 27 times 26 times 25, all the way down to 1. Okay, and in regards to what's going to cancel, and this will happen a lot of times, you'll see a lot of those terms canceling out. The 27 on down are going to cancel, so all of these factors will cancel out. In the numerator, we're left with 32 times 31 times 30 times 29 times 28. I'm going to get my calculator and figure out what that is. In my denominator, I have 5 times 4 times 3 times 2 times 1. So let's see, in the numerator, 32 times 31 times 30 times 29 times 28. That equals, is giant number, 23,331,840. In the denominator, 5 times 4 times 3 times 2 times 1, 120. Okay, and then again, now I'm going to divide these two to figure out what the answer is. So 23,000, hold on one second. me try that one more time. 32 times 31 times 30 times 29 times 28. I actually get a different number. I got 24. Sorry about that. Let me fix this guy up here. Erase. I get all right. Fix that. I got 24,000. 165,000. 24,165,120. Let me double check that. That looks good. And I'm going to divide that by 120. And I get 201. The answer to this, I get 201,376. So there's 201,376 different ways to choose to select 5 toppings for a pizza for a total of 32 toppings. Okay, so let's compare that with number 2. Excuse me, a combination lock consists of 30 numbers. You have to choose 4 numbers of the correct order to unlock it. How many possible combinations are there? I mean, this one I find hysterical because I hope you can tell that the word combination is incorrect to use when we're talking about locks, right? It actually should be called a permutation lock because in combinations, order is very important, right? Order actually matters. So that means that for these examples, we're dealing with permutations. So we have a total of 30 numbers. And from those 30 numbers, we're choosing 4 of them, and order matters. So this is the same thing as saying 30 factorial divided by 30 minus 4 factorial. Okay, so we get in the numerator, 30 factorial is 30 times 29 times 28 times 27 times 20, excuse me, times 27 times 26 times 25, all the way down. 30 minus 4 gives us 26 factorial, so 26 factorial is 26 times 25 times 24 times 23, all the way down to 1. And again, using the fundamental fraction, using the fundamental fraction rule, I don't have to click on that. Oh, let's use this guy, it's much prettier. We can cancel out the factors that are the same. So where do we start canceling from? 26, 25, 24, 23, 22, 21. So actually the answer is 30 times 29 times 28 times 27. I'm going to use my calculator for that. 30 times 29 times 28 times 27. And we get 657,720 as our answer for this one. So there are 657,720 possible combinations if you have a lock with 30 numbers and you want to choose 4 of those numbers in the correct order to unlock it. Let's take a look at number 3. Laura is going out for lunch. The lunch menu has a choice of 5 soups, 6 salads, and 3 pasta dishes. She has to pick 1 soup, 1 salad, and 1 pasta dish. How many different combinations can she choose? This is an example of the fundamental counting principle. So we would just do 5 times 6 times 3, 30. That gives us 30 times 3, which gives us 90. So there's 90 different possible combinations that she can choose. So what I really want to make sure you understand here is this notion of factorial and this notion that with permutations, we're concerned about order, position, or placement matter. And with combinations, just remember combinations, you couldn't care less about order. So the order is unimportant in combinations, and in permutations, position or placement are important. So one last thing I wanted to talk to you about before we kind of end this section is let's take a look at this idea of permutations of words. And what we mean here is if you have a word that has a certain amount of letters in it, like the word car, how many different ways can we write a 3-letter word using the letters car, using the letter C-A-R, where the word doesn't have to make sense? Okay, so we have 3 letters. We have C-A-R. That's one way we can do it. Well, we could also do C-R-A. Right, there's another way we can do it. We could also do, let's see, that's all we could do with C coming first. Let's do R first. We could do RCA. Another way we could do it is RAC. So we did all the ones with C first, all the ones with R first. Let's do all the ones with A first. We could do ARC. Ooh, look, we found another word in there, ARC. Or we can do ACR. And this is it. We have a total of 6 different ways that we can write the 3-letter word using the letters C-A-R. 1, 2, 3, 4, 5, 6. And it turns out that if we're trying to figure out how many permutations of words that we have with no repeats, we can just use the formula n factorial, where n is the number of letters in the word. So there's no repeats, right? CAR doesn't have any letters repeated. So that means we could have just done this, 3 factorial, which is 3 times 2 times 1, which gives us 6. And here are the 6 possible ways that we can do it. Well, let's take a look at this next example, which says, how many ways can the letters in the word math be arranged? All right, so what that means is we want to figure out how many ways we can write a 4-letter word using the letters in the word math. Well, first thing you should notice, there are no repeats, right? M-A-T-H, they're all unique. So all we have to do is count up the amount of letters, 1, 2, 3, 4. And it's the same thing as saying 4 factorial. 4 factorial is the same thing as saying 4 times 3 times 2 times 1, which gives us 24. So there are 24 ways that we can arrange the letters in the word math. Right? One thing, and let's just do 2 or 3 examples. Well, we could do M-A-T-H, or we could do M-T-H-A, or we could do A-T-H-M. Here's just 3 examples, but altogether, if we were to list them, there would be 24. And again, I didn't ask for a list. I just asked for how many ways we can arrange them. Well, let's take a look here and see what happens if we do have repeats. Let's take a look at this example. How many ways can we write the 3-letter word using the letters mom? Now, mom, notice here that we do have some repeats, right? So, excuse me, all of these letters are not unique. We have M, O, and then we're repeating them again. So let's list these and see if we can come up with them and then come up with a formula that would make sense that goes hand in hand with it. Okay, so one way we can do it is MOM. Another way we can do it is MMO. Any other ways? Well, notice that these M's over here, these are lookalikes, right? Here we have repeats. So we can't distinguish between which one's the first M, which one's the last M. So we wouldn't do MOM and MOM. Those two are the same. And we can also put O in the first position, so we could also do OMM. And that's it. So if you do have repeats, we have a lot less possibilities, right? In this example, a 3-letter word using repeats, we only have 3 possibilities instead of 6 like we had above. So there's a little bit of a different formula if we have repeats. And the formula looks like this. The permutations of words with repeats, and again, repeats means if the letter is the same, is equal to n factorial. So n is the number of letters in the original word. So here, there are 3 letters in the original word. So here's 3 factorial. Divided by, now here's the part we have to think about, n1 factorial times n2 factorial times n3 factorial all the way up to nk factorial. N1 represents the number of repeats for one letter, N2 represents the number of repeats for the next letter, N2, etc., all the way up to the kth letter. So what that means, if you take a look here, the denominator is going to look like this. If you have any repeats, which we do, you count up how many times it repeats, and you call that, so here M repeats twice, you call that 2 factorial. Because that's the only letter that repeats, that's it. We're going to leave it alone. Okay, and then when we multiply it out, we have 3 times 2 times 1. In the numerator, it's 3 factorial divided by 2 times 1. Cancel, 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 and we get 3. Okay, so let's take a look at this example, which said, how many ways can the letters in the word apple be arranged? Okay, so apple. So apple has 1, 2, 3, 4, 5 letters. So in my numerator is 5 factorial. And then the denominator goes however many repeats you have. So we do have a repeat because P occurs twice. So I'm going to call that 2 factorial, and that's the only repeat. 5 factorial is 5, 4, 3, 2, 1. 2 factorial is 2 times 1. Cancel these out. 5 times 4 is 20. 20 times 3 is 60. So there's 60 different possibilities for writing it this way. Okay, so here's 3 more examples for you. I'm going to give you guys a minute to read this. All right, let's try this one. Determine how many different 12-letter combinations can be made by using the word trigonometry. All right, trigonometry. Ready. How many letters? Oh, there's going to be 12 letters. So it's 12 factorial in the numerator. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, in the denominator goes repeat. Let's take a look at a t. T repeats. T repeats twice, so we're going to call that 2 factorial. R repeats twice also, so we're going to call that 2 factorial again. I does not repeat, G does not repeat, O repeats twice, so we're going to call that 2 factorial. N does not repeat, M does not repeat, and we have no other repetitions. So however many times it repeats, for however many letters you have, this is what you want to do on the bottom. Okay, so 12 factorial. 12 times 11 times 10 times 9 times 8 times 7 times 6, 9, 6, 5, 4, 3, 2, 1. You get the general idea. 4, 3, 2, 2, 1. That's the numerator. And the denominator 2 factorial, 2 times 1. 2 factorial again, so times 2 times 1. 2 factorial again, so times 2 times 1. Okay, so let's do the numerator. 12, if you multiply 12 all the way down to 1, let's see what we get. 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I get 479,001,600. Okay. And then in the denominator, 2 times 1 is 2, times 2 is 4, times 2 is 8. So in the denominator, we get 8. So when we divide that by 8, we get, so I'm going to put the answer up here. I'll leave some more space for the next worksheets. I get 59,875,200. Okay, so that's the answer for that one. All right, let's take a look at number 2. Determine the number of different 7-letter combinations that can be made using the letters monkeys. 1, 2, 3, 4, 5, 6, 7. 7 factorial. In terms of repeats, we don't have any repeats, so that's it. It's just 7 factorial. Again, I'm going to get on my calculator. 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1, which gives us 5,040. And here's the famous question that everybody asks with this type of example. How many different 11-letter words can be made using the letters from Mississippi? Well, again, in the numerator, we have 11 factorial, because we have a total of 11 words. Now let's hit all the repeats. M occurs once. I occurs 1, 2, 3, 4 times, so that's 4 factorial. S occurs 1, 2, 3, 4 times, so that's 4 factorial again. We already did I and P occurs twice, so it's 2 factorial. Okay, so in my numerator, 11 factorial, and I'm just going to start doing this on my calculator. I should have the hang of it by now. 11 times 10 times 9 times 8, excuse me, times 7 times 6 times 5 times 4 times 3 times 2 times 1. We get 39,916,800. In the denominator, so 4 factorial, that's 4 times 3 times 2 times 1, and we're multiplying that by another 4 factorial, so times 4 times 3 times 2 times 1, and then we're multiplying that by 2 factorial, so times 2 times 1, and we get 1,152. Okay, and when you find the quotient of these two, I'm going to go back and put this in my calculator, 39,916,800. Divided by 1,152, we get 34,650. So there's 34,650 ways that we can make 11-letter words from the letters in Mississippi. And the reason that it's small is because there's a lot of repeats in Mississippi. Okay, so thank you very much. And you're now equipped to do your next homework assignment.